Okay guys, let's take a look at today's lesson. In the first part of the unit, we went through and looked at derivative things, a lot of different derivative things, differential equations and slope fields, approximations for differential equations, a visual approximation by slope field, a numeric approximation by Euler's method. We are kind of changing gears and we're going to look at area and volume this week. First off, we're going to look at area. We are familiar with area. I think of the lessons, this one's probably the most straightforward because you already have some experience with area. We have been finding area under a curve. If we think about it, if we just look at this piece right here, we've been finding area under a curve of one curve. That's what we've been doing, area under one curve. Where we're going today is we're going to actually find the area between two curves. That's where we're going. So let's talk about that. There's a formula involved. This formula is the formula with respect to x. Area is, the bounds would be either where the two curves intersect or some preset bounds like from 2 to 5, some bounds. You'll have bounds here. Then it's the f of x is the larger function. And larger, what I mean by larger is the y values are larger in the certain area than the x values. So it's really big minus little. If we look at this picture, it's pretty clear that from A to B, the blue one, which they're titling f of x, is the larger function. Everywhere I look, every vertical place I look, the y value here is bigger than the y value there. That's how we judge which one is bigger. So here, all the y values on the blue one are larger than all the y values on the yellow one. So this would be our big minus little. And I think that makes sense to us. We're used to seeing things with respect to x. That's not unusual for us. I think where we have a little bit more trouble is with when we're with respect to y. When we're with respect to y, it's the same formula, big minus little. But big is a little bit harder for us to visualize. We're not used to looking at it this way. Here, notice big, I looked at the biggest y value here, right? Big, this y value is bigger, y value is bigger. When I'm with respect to y, which value you think I'm going to be looking at to be bigger? X. I'm going to see which x value is bigger. So here, the curve that's farthest to the right is going to be the bigger one. So if I'm looking, along this way, here I was looking at vertical lines, here I'm looking at horizontal. This x value is larger than that x value. And this x value is larger than this one. So therefore this curve they call f of y is the larger function. F of y minus g of y. So that's basically the concept. It's just going to be the biggest one minus the smallest one. Now you can imagine that there will be times where maybe they change places. These are pretty straightforward. This one, in this case, this f of x is always larger. In this case, this f of y, well, here you see they changed places. Now this one is larger. In this particular case, yeah, this is going to continue on. Here, between the intersecting points, f of y is larger, but as we go to where they don't intersect, g of y is larger. So you can imagine it's going to be really important to see a graph of what you're getting ready to calculate. You need to be able to see and tell, is it always the larger one? Does it change places? So graphs are going to be really important. In fact, on each one of these, even if you're using a calculator, I'm going to want you to sketch the graph for me, even if it's off of your calculator. That on a quiz or a test would be like worth a point. The graph is going to be worth a point. Okay, so we're going to graph all of them. Alright, so that's the overview. Any questions on just the concept so far? I have two problems that I want to work. Okay, let's look at the two problems. Alright, on the first problem, it's not graphed for us, so we need to graph it. Usually the ones that you're going to be graphing are if you don't have a calculator, they're usually going to be ones you can easily graph. They're not going to be really crazy ones. So here we have y equals negative x. I'm going to graph the line first just because that's easier to graph. So there's my y equals negative x. Then I have y equals 2 minus x squared. So that's an upside down parabola translated up 2, right? So translated up 2, upside down parabola. I only care about the region enclosed by these two. So I'm really only interested in this piece. Certainly I can go ahead and draw that piece if I want to, and I have some questions earlier. What about this area in here? Do I have to calculate that? Well, is this area ever going to stop? No. This is an infinite area. They're never going to cross again. So this would be like infinity. I mean, there isn't an answer to it. When it says area enclosed by the curves, it means closed. It's closed in. It's not open. This portion right here is closed in. That's the area that we're going to be calculating. Now we have a choice. We can do it with respect to x or y. It's typically your choice. When looking at this, it would be much easier to do this with respect to x. So that's the way we're going to do it. Now I'm going to show you how you could do it with respect to y, just so that you know. I mean, you're going to get the same answer as long as you've done it correctly, either way you do it. With this, it's pretty clear that the parabola, if you look at each vertical space, everywhere I compare the parabola to the line, the parabola is bigger. Everywhere. You with me? I'm doing it with respect to x. So we're looking at which is the biggest y values. Everywhere I look, it's the parabola. So we're going to use the parabola. We're going to use it with respect to x. Now, on your daily work, I really want you to use calculators. I used to start this out where we did them by hand, but really what I want to see is I want to see you write the integral out, and then I want you to use your calculator, okay? Because I want you to be able to get more problems done. So that's what we're going to do here. We're going to write the equation out, the integral out, and then we're going to put it in our calculator and see what the answer is. So let's look. So we decided, well, and another thing, so these intersecting points, well, I can tell pretty easily what they are because I graphed it, right? They're integers. What would happen if it wasn't so easy to tell? Maybe they're fractional. How do we find intersecting points? We set them equal to each other, right? We set the equations equal to each other, find our intersecting points. So that's done for us already here. So we're going to go from, and these are x bounds because I'm doing it with respect to x. We're going to go from -1 to 2. We agree, I believe, that the parabola is the bigger one the whole time. So I'm going to put the parabola first, 2 minus x squared minus, and then the smaller one is the line, which is a -x dx. So on a problem, I want to see the graph. I want to see the equation right here, your integral. Then it's just a matter of putting that integral in your calculator and allowing the calculator to do that. And you should get 9/2. Okay, we could certainly do it by hand. It wouldn't take that long, but for time issues, I would like for you to use your calculator. You also need to get very adept at using your calculator. So we're going to use this week, on all the stuff we're doing this week, area, volume, you're going to be using calculators. All right, so I do want to show you how to set this up with respect to y. Okay, just so that you see. It is much more difficult to set it up with respect to y. Okay, but we're going to do this. So let's look, with respect to y, it's the farthest, the one that's farthest right is the bigger one. Okay, and I would actually have to split this into two pieces. And we're going to talk through why. I would have to do this area and then the area on top. So let's see why. On this area, the parabola is larger than the line. Right here, right? If you look, again, we're looking at horizontal lines. Everywhere I draw a horizontal line, this x value on the parabola would be larger than the one on the line. You agree with me? Okay, so I would set up the integral from, let's see, my y value is -2 up to 1 from the parabola, and oops, of course I'd have to solve for x. So this would be x equals negative y, and this would be a little bit of work. Let's see, so that's x squared equals 2 minus y, or x equals plus or minus square root of 2 minus y. So we'd have to make sure we're in terms of x equals to do it with respect to y. All right, so this part of the parabola is which one of these radicals? Is the positive one. We're on the right side, so it's a positive one. So I would have to do parabola, which is the square root of 2 minus y, minus the line, which is negative y dy. Okay, that would be one integral if we were doing it with respect to y. The other one would be this kind of weird thing. Look, it's the radical is bigger than the radical, than itself. See, if I compare, I'm comparing horizontal. When I look horizontally, this one is bigger, that one is smaller. So this one is represented by the positive one. I'd have to go from 1 to 2. So the positive one is square root of 2 minus y, minus this side is represented by the negative radical, the negative 2 minus y dy. Do you see why it really makes a big difference which one you do it with respect to? If you type this in your calculator, you're still going to get 9/2. But doing it with respect to y is much more difficult because of the way that it's set up. Now, some of you may, and I'm sure some of you are looking at this like she's lost her mind. I have no idea what that is. I'm going to ignore the red part. I'm only going to worry about the blue part. Okay, that's fine. But I need you to see that you can do them either way. One just typically is much easier than the other way. Okay? All right, we'll let that sink in. Yes? Okay. Right here, this side is the square root of 2 minus y. This side is negative square root of 2 minus y. Okay? This side, the purple side, is always bigger than the orange side because we're with respect to y. We're looking at horizontal. Right here, this x value is always bigger than that one. That is why this is the bigger one minus the smaller one. Okay? My bounds are y bounds.
Oh, there you go.
Okay? Because why? Because I'm with respect to y. Okay? My y bounds are with respect to y, x bounds are with respect to x. Okay? All right. Okay, we're good. Moving on. Again, if this red one troubles you and you would like to talk to me about it after the notes, I would be happy to continue to help you with that one. I needed you to see that it makes a difference and you have to be very careful. Okay? Let's do our second example. This one they graphed it for us, which was very kind of them. They didn't give us all the intersecting points, so I guess it wasn't so kind. We don't know about this intersecting point, but we know how to do intersections, right? We just set the equations equal to each other. So let's start out by finding this intersecting point. I would say x squared minus 4 equals negative x squared minus 2x. Now, even if you do this in your calculator, it's fine, okay? It's fine if you have a calculator and do it in the calculator. But I need to see, and they will too, they want to always see the setup and the answer. You cannot just write answers. You say the setup, this is what you're doing, and then you do your intersections, and this can actually be done by hand, but since we're working with the calculator, you're going to get x equals negative 2 and 1. That's what you're going to get. When you intersect them in your calculator, that's what you're going to get, negative 2 and 1. We actually already knew about the 1 intersection. They were kind enough to give us that one. This one is the negative 2 intersection. And so our intersections are set. Now let's write our integrals. Notice that from negative 3 to negative 2, the blue one is the larger one. Now I'm going with respect to x. I think with respect to y, you could certainly do it, but it would be nightmarish. I'm just saying. Okay? It'll be nightmarish. So I'm going with respect to x. So we have our first integral from -3 to -2. The larger one we have identified by the graph is the blue one, which is x squared minus 4. We subtract the smaller one, which is that pink one or red one, which is -x squared minus 2x dx. That's our first integral. That will take care of the area of the first piece. The area of the next piece. Our bounds go from -2 to 1. And in this case, the pink one or the red one is bigger. -x squared minus 2x minus, and then the blue one is smaller, x squared minus 4 dx. We put that in our calculator. This one would actually take a bit more time by hand. It's certainly possible. I actually did that one by hand, but we put that in our calculator, and when all is said and done, you should get 38/3. Now let's talk about the answers. Every answer you get is always positive when you're doing the area between curves. Because why? Because I'm always doing biggest minus smallest. It's always going to be positive. Biggest minus smallest. If you get an answer that's negative, that should immediately alert you to the fact there's something wrong. When you're doing area between curves, you will always get a positive answer because of the nature of the formula. It's always big minus little. Okay? So, just so that you are aware. I think that pretty much wraps up our lesson. Is everybody okay? Okay.